Welcome back. Episode 10 ECU level threats. Episode 9 covered external interfaces, how attackers reach the vehicle. From the outside, this episode goes one layer deeper: physical possession of one ECU, and what that means for every other vehicle of the same model. Before anything else, anchor this concept. ECU-level vulnerabilities are fleet-specific, not device-specific. Reverse engineer one ECU from a scrapyard, and every vehicle of that model running the same firmware is exposed. One bench, millions of targets. Let's go. 5 attack categories. 1 debug ports. JTAG, UART, SSA. Development tools left open. In production. Trivially exploitable. 2 flash programming attacks. The non-volatile memory holding. Firmware, calibration data, and keys a direct target when the programming interface is not locked after manufacturing. 3 bootloader vulnerabilities. The secure boot chain is the root of trust. Break any single link in unverified code runs. 4 software reverse engineering. Offline, unlimited time, no defenses apply. Everything inside the binary gets mapped. 5 key extraction. Side channel analysis and fault injection. Recover cryptographic keys from the hardware directly. Critical note at the bottom: unlike a network attack, ECU level work needs only one physical device. Findings from that device scale to the entire production fleet of that model. 3 debug interfaces, all devastating when left active in production. JTAG is the standard hardware debug interface in embedded systems. In development, it is essential. In production, it is a vulnerability. With JTAG, an attacker halts the CPU and reads RAM directly, capturing live cryptographic key material in plain text. They extract encrypted firmware by reading RAM after the CPU decrypts it at boot, bypassing the flash encryption entirely. They access eFuse and OTP, where root public keys are stored, and in some implementations can permanently replace those keys, collapsing the entire secure boot chain from its foundation. UART debug shells are equally dangerous and even cheaper to access. A development serial console left in the production firmware, a $10 USB adapter and the right baud rate, unauthenticated terminal access, full memory dump capability, privileged commands with no password. On SoC-based ECUs, Ivy, ADAs, Telematics SSH, and Telnet shells, installed for engineering convenience, are frequently left in production firmware with default root credentials. An attacker who pivots onto the vehicle's internal network from any external interface may find these shells reachable without ever touching the physical hardware. Inventory every debug interface. Lock or remove it before production. Penetration test this before every single release. 3 attacks against ECU flash. Serial flash interface abuse. The factory programming interface is not hardware locked after production. An attacker probes the flash IC, reads the full firmware binary. Encrypted firmware is captured in plain text from RAM at runtime. No need to break the encryption algorithm. Residual flash library abuse. Erase and program functions compiled into the production binary and never removed. A malicious application with code execution calls them directly. Selective calibration erase, full firmware wipe, or repeated NAND erase cycles that permanently brick the ECU. Calibration data tampering. Calibration defines behavior. Torque curves, emission thresholds, safety limits. No integrity protection means an attacker writes directly to flash. Emission defeat. ESC threshold removal. Limiter bypass. This is the Dieselgate mechanism applied to any ECU with an unprotected calibration partition. 5 stages in the boot chain: boot ROM, Stage 1 bootloader, Stage 2 bootloader, OS kernel, application code. Boot ROM is mask ROM, the immutable root of trust. Each stage verifies the next. Break any link. Everything above runs unverified. 3 attacks. Glitch attack EMFI. Attacker replaces flash with malicious firmware, then applies a precisely timed electromagnetic pulse to the CPU. Target the conditional branch evaluating the signature result. The code if hash mismatch halt. The EMFI pulse causes the CPU to skip that halt instruction. Malicious firmware executes despite a failed signature check. Documented, reproducible. Demonstrated against production ECUs. Rollback attack. No monotonic version counter in the bootloader. Attacker replays a legitimately signed OTA bundle from an older version containing a known vulnerability. Vehicle reverts. Patch removed. Exploit re-enabled. Residual attack. Flash erase and program routines not cleared after. The update completes. Malicious code calls them directly, writing to the firmware partition with no authentication. 5-stage pipeline after firmware extraction. Step 1 acquisition. JTAG read UART dump, flash desoldering, OTA capture, or a leaked update file. Step 2 identify architecture. CPU family, NDNS, memory map, AUTOSAR BSW layer fingerprints. Step 3 decrypt. Runtime JTAG RAM dump after boot decryption, or a glitch attack to force unencrypted execution. Step 4 binary analysis. GIDRA or IDA Pro. Map every security critical function UDS handler, seed key algorithm, CAN parser, secure boot verification. Unlimited time. Full binary. No defenses apply offline. Step 5 vulnerability discovery. What they find hard-coded symmetric keys never rotated from development. The UDS 0x27 seed key function identical across every ECU of that model in the entire fleet. The CAN message database equivalent every signal mapped, enabling targeted injection with zero guessing. Buffer overflows in message parsers fixed stack buffers with no-length validation on network-supplied data. Once found, building an exploit is engineering, not research. 4 techniques to recover keys from hardware. ISPA simple power analysis. 1 power trace during an RSA or ECC operation. Without countermeasures, key bits 0 and 1 produce. Visually distinct consumption patterns directly readable. Equipment costs $500. DPA differential power analysis. Thousands of traces plus statistical correlation. Works against AES 128 without countermeasures. Automotive targets, CMAC AES keys and SECOC. Symmetric keys and flash bootloaders. EMFI electromagnetic fault injection. Active attack. A timed EM pulse skips instructions or corrupts registers. Against secure boot bypasses the verification branch. Against running crypto forces error conditions that leak key material. Through observable output changes. Supply chain and software leakage. Development keys left in production firmware. Known answer test keys, predictable constants for hardware. Verification never replaced with production values. Worst case, an insider installs an attacker-controlled root public key. At the provisioning station, every vehicle produced after that point accepts attacker-signed firmware. 1 breach. Permanent fleet access. 5 steps. 1 scrapyard ECU to fleet-wide compromise. Step 1, purchase from a scrapyard. $50 to $200. No vehicle ownership. Lab bench, unlimited time, no pressure. Step 2, locate the JTAG header on the PCB. Halt the CPU. RID RAM live key material captured in plain text. Full flash dump, including encrypted partitions. Step 3, load binary into GIDRA. Identify architecture. Decrypt using runtime RAM dump. Locate the UDS 0x27 seed key function. Extract hard-coded fleet-level keys and crypto seeds. Step 4, build the toolkit. Backdoored malicious firmware. A key generator for valid 0x27 responses against any seed. An automated DUX34 and DUX36 flash script. Step 5, deploy. Any infield vehicle of the same model, OBD port. Generator produces the correct DUX27 key. Script flashes malicious firmware. No signature verification stops it. Every ECU of that model shares the same algorithm. The entire fleet is exposed. Root Insight ECU vulnerabilities are fleet-specific. 1 bench unit scales to every vehicle of that model on the road. 4 categories from Handbook Chapter 9. Debug port hardening. Permanently disable JTAG and UART by blowing the eFuse after production programming. A field debug must be preserved, authenticate with a device-unique PKI Certificate 1. Per ECU, non-transferable. Remove SSH and Telnet binaries from the production build entirely. Verify with penetration testing. Flash and bootloader protection. Hardware write protect flash after production. Remove erase and program library code after use hard. Removal, not a build flag. Secure boot with ECDSA at every stage. Anti-glitch coding. Hamming distance constants. Redundant conditional. Checks. Execution flow monitoring. Test against EMFI before shipping. Reverse engineering mitigation. Encrypt firmware at rest with AES 256 and an HSM managed key. Use the HPSE for all key operations raw keys. Never in general purpose RAM. MPU and MMU isolation for security. Partitions. Key extraction countermeasures. All long-term keys in the HSM hardware. Key store exclusively. Power analysis countermeasures random delays. Operation blinding, constant time code. Strict key lifecycle, no. development or KATI keys in production, verified during manufacturing. 4 things. Carry these into every project. 1 debug ports locked before production, no exceptions. JTAG, UART, SSH in production firmware are critical vulnerabilities. Blow the eFuse. Remove the binary. Penetration test before every release. 2 secure boot plus anti-glitch hardening both required. Verifying the signature is not enough if the branch is glitchable. Hamming constants, redundant checks, EMFI testing. All 3. 3 assume firmware will be extracted. Design accordingly. Reverse engineering automotive ECU firmware is routine. Encrypt at rest. Keys in the HPSE. Never let a cryptographic key live in general-purpose RAM. 4 one-bench ECU compromised equals the entire fleet at risk. Same. 0OX27 algorithm fleet-wide means 1 scrapyard unit hands and attacker keys to every vehicle. Per device unique keys. UDS NAC 29 PKA. Integrity-protected calibration data. All 3 together required. That is Episode 10. Episode 11 takes everything from the threat landscape into structured analysis Terra in practice, asset identification, threat enumeration, risk scoring, control, selection. See you in Episode 11.